This video showcases the workings of a compact, highly reliable I-to-P transducer provided by M-System. Pneumatic actuator-driven control valves and dampers are still widely used in plants. These pneumatic actuators are typically operated in the range of 20 to 100 kilopascals or 3 to 15 psig, which are standard signal ranges used globally in instrumentation systems. Conversely, the control output of DCSs, PLCs, and controllers use the standard electronic signal range for instrumentation of 4 to 20 milliampere DC. An I-to-P transducer is an industrial instrument that plays a vital role in converting this standard electronic signal range into the standard pneumatic signal range and interfacing with both types of instrumentation. While I-to-P transducers are generally known for having long delivery times and have recently been discontinued by numerous manufacturers, M-System is one of the few remaining manufacturers to have consistently maintained short delivery times for some 40 years and counting. First, let's look at where the I-to-P transducer is used. This is a simulated plant facility named Plantlet, installed at the headquarters of M-System. Plantlet employs a flow control loop using a pneumatic control valve. The I-to-P transducer, model HVPN, is installed here. The 4 to 20 milliampere DC control output from the multifunction PID controller, using the flow signal from the electromagnetic flow meter as an input, is connected to the input terminal. Once the instrument air supply is received from the mounting block, the pneumatic signal is output from here. This HVPN is a loop-powered I-to-P transducer that can drive all electronic circuits with a 4 milliampere input signal. It does not require a power supply. With a compact size that is just 25 millimeters wide, the HVPN fits neatly into a junction box. The HVPN converts a current input signal into a proportional 20 to 100 kilopascal pneumatic signal to drive the pneumatic control valve. Next, let's look at how the I-to-P transducer converts the input electrical signal to a pneumatic signal. This is a diagram illustrating the operation of the pilot valve and other major parts. The pilot valve interior is split into 3 sections by 2 diaphragms connected by discs. Air passing through an orifice flows into the uppermost section and is then ejected from the gap between the nozzle and the flapper. When doing so, the air pressure received by the upper diaphragm is referred to as back pressure. The gap between the nozzle and the flapper is operated by a force motor, which can greatly change the amount of back pressure through minor alterations in the gap. The output of the electronic amplifier driving the force motor is proportional to the deviation in the input signal, and the output air pressure feedback signal detected by the semiconductor pressure sensor. In a state of equilibrium, this deviation is 0, and the output air pressure feedback signal matches the input electric signal. As the input signal increases, the force of the force motor will work to close the flapper. This will increase the amount of back pressure, which presses down on the diaphragms, and then the plug in turn. The air supply will flow from the underside of the plug and increase the amount of output air pressure. The output air pressure is detected by the semiconductor pressure sensor and fed back to the force motor via the electronic amplifier. A matching input signal and output air pressure will result in a balanced state. Conversely, as the input signal decreases, the force of the force motor weakens, causing the flapper to open. This will decrease the amount of back pressure and allow the diaphragms to push back. When the diaphragms are pushed back, a gap will open between the top of the plug and the discs, from which output air will escape and lower the output air pressure. The output air pressure is detected by the semiconductor pressure sensor and fed back to the force motor via the electronic amplifier. A matching input signal and output air pressure will result in a balanced state. Let's take a look at the inside of an actual I-to-P transducer. This is a force motor. The nozzle flapper assembly is found here. This part is the pilot valve assembly. This is a semiconductor pressure sensor equipped with a temperature compensation circuit for converting the output air pressure to an electrical signal. The output signal from the semiconductor pressure sensor is input to the electronic amplifier, which drives the force motor to form a feedback loop via an electrical signal. This electronic feedback system, pioneered by M-System, provides substantially greater loop gain compared to conventional mechanical feedback systems, and allows for a high-precision, stable pneumatic signal that is unaffected by nozzle flapper and pilot valve characteristics. There are also no positional errors. Next, let's look at how M-System's production line achieves the high performance and high reliability of its I-to-P transducer while incorporating these complex assemblies. The purchasing and production section inspects each and every key part, such as the electromagnetic flapper assemblies, which combines the force motor and nozzle flapper and the semiconductor pressure sensors. Due to the high degree of variation in individual characteristics, the electromagnetic flapper assembly undergoes checks of its signal rise, hysteresis, and other characteristics, in addition to checking output signals for 0% and 100% input. Pressure sensors are also stored in a thermostatic chamber at 80 degrees Celsius for 10 days to screen for output deviation before and after the storage period. Following this, the quality assurance section removes certain samples and ages them in varying temperature conditions over a 10-day period as part of acceleration tests to check for output deviation. Following product assembling and calibration, products are checked one last time for abnormalities in linearity and the effects of supply voltage, supply pressure, and mounting position. Only I-to-P transducers that pass these stringent testing processes at each step of the manufacturing process are shipped. Pneumatic instruments are still widely used in power generation, chemical, petrochemical, and pulp and paper plants, as well as plants in various other fields. In addition to operating pneumatic control valves and dampers, I-to-P transducers are used to remotely control pneumatic indicating controllers via a DCS. P-to-I transducers are used to convert pneumatic signals from old pneumatic field instruments into electrical signals that can be sent to a DCS. Use of I-to-P transducers and P-to-I transducers offer a cost-effective way to utilize existing assets in the field. M-System offers a large lineup of I-to-P and P-to-I transducers tailored to every application, including plug-in types and rack-mounted types. Since first launching its I-to-P and P-to-I transducers some 40 years ago, M-System has supplied a total of more than 189,000 transducers. M-System also remains dedicated to keeping its promise of short delivery times. You can rely on M-System. We will continue to develop products without discontinuing models that have already been released to the market. Thank you for watching.